Yeah, that I have given some thought to. Um, and that's about it for Casper.
Cool.
Vlad, you?
So this week, I've been working on. I made progress on liveness proof and on um, this validator rotation thing. And
Uh-huh.
I'm not sure if I gave an update about this new lower bound. I think I did last time. The lower bound on the adversary, where you kind of look, make sure everyone has the same estimate, sees from each other the same estimate, and can't see from each other different estimate.
Right. Yeah. You checked
Okay.
out. Yeah.
Right. And so the only things I really have to talk about for the update are the validator rotation and liveness proof stuff,
Mhm.
which is all pretty cool stuff. I guess let's do the wide then deep. Does anyone else want to give a little overview of what their update's going to be about?
Sure. I still working on a testing framework and got some nice pretty colors on displaying kind of fault tolerance, but that's pretty much it.
Oh yeah, that's actually really cool. You can actually like see the blocks being finalized in this like view of the blockchain, based on the different colors, and like you can tell how finalized they are.
Yeah.
My update is going to be on the implementation of a testing language for Casper, basically. So you can describe different states and state transitions for Casper and just, concisely. Like my new block, prepare commit.
Cool.
Sweet. Yeah. So I guess I'll go ahead and talk about the validator rotation thing, and then maybe we'll talk about the liveness thing. So I came up with a pretty cool way to do validator rotation. So the validator rotation stuff that we're kind of familiar with in some way is the stuff that Vitalik wrote a blog post about, where basically the old validator set and the new validator set would each kind of with finality like sign the transition, and then the kind of new validator set would take over. And there's kind of this like passing the torch with consensus that protocol does. I hear myself. I hear a strong echo all of a sudden. I'm not sure who that is. Testing. Okay, cool. I don't hear myself anymore. What I was able to come up with is a way to do validator rotation without consensus, and it's pretty cool. It basically just works like this. I'm going to assume that everyone's familiar with the 4-choice rule for the kind of correct by construction Casper the Friendly Ghost. But maybe I'll cover it. Basically, there's a set of validators. They have weights, and then according to the latest blocks from these validators, their weight contributes to the blockchain that is, with their latest block as the head of that chain. And then the way the 4-choice rules works is you start off the last finalized block, and then you pick between the children of that block based on which one has the most weight, according to these latest blocks from each of the validators. And then you go to the best child, and then you ask which one of those the children of that child have the best weight, have the most weight. Still according to the latest messages from the validators. And then you can kind of iteratively do that, making a single block choice at a time. And so the way that works is basically like, in the context of this weights map, right? Which kind of says, okay, like here's the validators and here's their weights. And now what's going to happen now is basically instead of having that weights map be in the background, kind of as part of the protocol, it's going to be actually specified in the blocks. So the Genesis block is going to include the weights of the validators who are going to be choosing between the children of the Genesis block. And then like the all of the children of the Genesis block are themselves also going to specify the weights that are going to be used to choose their children. And the 4-choice rule works very similarly, only instead of having the same weights that you use all the time, you basically will like look at the block and see what weights to use for choosing between the children on that block. The Genesis block tells you how to choose between its children. The children of the Genesis block tell you how to choose between their children, and kind of so on. So it's still a deterministic fork choice rule. Given any two clients with the same view will come out with the same fork choice, regardless of the order that the messages arrived, because the blocks will give the same weights mapping, and they will have the same latest messages from each of the validators from each of the mappings, and so they'll make the same decision, or the same fork choice. So it's deterministic, which means that the estimate safety implies consensus safety proof holds, and then the only next thing to show is that it can somehow get stuck. And that's quite straightforward, because the fork choice rule is basically exactly the same as the fork choice rule before, except for now the weights are kind of changing between every height rather than being just fixed. And what that basically does is it basically means that imagine to have some latest messages that finalize the choice of the first child of the children of the Genesis block. Then those latest messages also would finalize the choice of the children of the Genesis block under this new fork choice rule, because the new fork choice rule is the same as far as a single step is concerned. The difference is that between the steps, the weights mapping changes. So at this point, I guess I want to stop for questions before I kind of continue some commentary on this thing. Anyone? Okay, well, I guess I'm going to assume that everyone hears me and everyone understands, because no one's saying anything, and so I'll just move on. A few notes. So one of them is that actually you don't actually need to change, the validator set doesn't actually need to be changed every block. This is just kind of to demonstrate that it can. We could just say, oh, it changes every few hundred blocks or whatever. The important thing to notice is basically that there's no consensus, right? The block itself just says who the next validators are. And then in practice, what this is going to be is that there's going to be some smart contract, which determines who has deposits and rotates them out, and that's smart. And then every block will have a root hash for the state, which will include this smart contract, which will give the weights function. And so when I say the block has it, I mean just from the point of view of the fork choice rule, the only thing that I need to know is that from every block I can get the weights. In practice, there's a lot more going on, but as long as I can get the weights for every block, then I can make this fork choice rule, and because that fork choice rule is deterministic and can get stuck, then it's safe. We have all the safety that we possibly need out of a fork choice rule with validator rotation, which is quite cool. And then the next kind of the kind of conceptual change that happens here is, rather than having this property that when the choice of a child is finalized, all of the ancestors of that child, i.e. the whole blockchain with the head as that child, being finalized is no longer really the case. The thing that's finalized now in this model is which child is the best one for this block, for which block. And if, say, we have that for every block, then we're able to draw a blockchain. If, say, imagine we don't have finality for a choice between two children of the Genesis, but for each of those children, we have the distinct weight maps, and we do have finality on two different choices of blocks. That's something that totally could happen here. And the first set of the validators for the first height could potentially oscillate between these two children, each of which have themselves finalized children. So we don't kind of have this case that finality on later heights necessarily means finality at lower heights, which we did have with Vitalik's protocol. But the difference is that Vitalik's protocol requires that there is finality in order to change the validators, whereas mine doesn't. And so that's kind of natural in that way, because like, I mean, I don't require finality, therefore we don't necessarily have finality when we move before we move on. Another thing that's interesting is that there's no way to actually have the later validators provide any finality to the earlier heights. And this is because it has to be the case that if the earlier height validators finalize a block, then that is kind of binding for later heights. But what that means is that if the later heights finalize it, they have to do it in a way that agrees with the earlier ones. However, the earlier heights could, the validators, the earlier heights could potentially finalize two conflicting states by just being sufficiently Byzantine. And in that case, there's no correct decision for the future validators. And moreover, the fault tolerance that of the bottom layer is really the only fault tolerance that exists. So imagine that the choice of children was finalized with like say 2 fault tolerance, and then like we have like 3 faults, and now it's finalized again with like 1 fault tolerance, but like for a different choice. Then in that event, any future fault tolerance that is contributed by later validator sets, clearly like actually wasn't real, because it only took like 2 faults to change the choice at the bottom level from being like finalized on like one of the blocks to being finalized on the other. And that bottom layer really does need to have priority, because otherwise finality at the bottom level just means nothing, because future heights can revert it. And so basically, I'm able to do validator rotation without consensus, and doing validator validator rotation without consensus is interesting, because it means that we don't need to have a fault tolerance threshold in the protocol, and we can move like all of the safety thresholds outside the protocol, which is, I think, a really elegant thing, and it's one of my favorite things about Bitcoin actually, is that you just wait 6 confirmations, but the protocol doesn't actually say how many confirmations to wait. Whereas like in traditional consensus protocols, it says like, oh look, we chose a 3rd fault tolerance, and like everyone makes a decision after like a 3rd faults are required. So that's pretty exciting. I think I'm opening it up for questions again.
Yeah, that's super cool. One question that I had was, is there so if you were to be a kind of normal validator, right? You said that like in Bitcoin they just choose six faults. Like, do you have any kind of sense for what would be a reasonable kind of rule to follow or heuristic to follow?
Well, I mean, yeah. I mean, the heuristic is pretty simple. Like, you look at the blockchain, you see how much security you normally get, and then you like pick that. You like just like watch the blockchain and see how much fault tolerance it produces. And like if it tends to produce like always over like 80%, that like sometimes it goes up to like 99, 98, then like you just insist that you require 80% fault tolerance for a decision. So basically what I'm saying is like we should be greedy and optimistic, rather than a priori pick a number.
I see. Cool.
And an interesting thing is that you imagine what if some validators at some height never finalized, like what gives, what ends up happening, and basically the answer is we can at the end of the day anyone can just kind of via just subjectivity, which means like okay, you don't really have determinism anymore, which means that there's not necessarily consensus safety just due to our like normal proof. Just decide that like you're never going to choose that fork over this one, and as long as there's synchrony, then that's going to be safe. In an asynchronous network, that's not safe. But luckily for us, we get to have like the protocol running and also have a community around it who is able to talk to each other, and so we can kind of see and agree with each other that we all kind of see this block, this non-finalized blockchain made by these validators, and therefore kind of all choose that in the future, even if later the validator set becomes active and changes their mind. So with synchrony, we end up making up some of the ground that we can't actually make up, or we can't actually cover in an asynchronous context. Hopefully that's somewhat clear.
Yeah.
Cool. Well, maybe someone else wants to give an update, and then I'll try to get to my liveness proof later.
Yeah, I can go for it. If you guys want to see some pretty colors, I can share a screen real quick for like.
Do we?
Sounds good.
All right, give me a second. It's still getting completely sorted out, so there are some unsolved bugs as of now, but things should work. So we're kind of just have random message propagation, and what we'll see hopefully is that kind of cool. So kind of message increase in color intensity. So colors subject to change, but kind of we have yellow here and then a little bit darker yellow here, right? And so this kind of tells us, this has some fault tolerance, and this is like a little bit more fault tolerance. And if we run another round, we should see we even get more. So we didn't here, but you can see the yellow expanded. Oh, we're missing it. Where is it at? Yeah, so you can see like this is all going to dark yellow now, but we haven't gotten darker fault tolerance, at least detected by this oracle here. And now we finally have it. So you can kind of see it. It kind of, it just in an interesting way, it kind of moves like a snake, right? And so it like, it slowly starts finalizing everything, and the fault tolerance kind of builds on past blocks as more later blocks get made, which is just pretty interesting to watch. Here, I'll run it a bit more. Yeah, and then black is kind of like our max level fault tolerance, so it can withstand like n-1 kind of faults in this view, in the global view, which is pretty cool.
So yeah, this is amazing. So basically, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks that are finalized with maximum fault tolerance, and 12 blocks that are finalized period with 20, 30, 46 messages, or 46 blocks. So that's pretty cool, right? Pretty stoked about that. And basically, like, as you keep going, the like ratio of finalized blocks to messages will just continue approaching 1, I think, or some constant that, like, oh yeah, look at all those finalized blocks on the right there.
Yeah, it's cool looking for sure. Cool. Yeah, so that's pretty much that. Other than that, I've been working on the testing framework. Kind of a cool thing that I've been doing is, so the lower bound and the safety oracle that Vlad described like 3 weeks ago or something, and I implemented like 2 weeks ago or something, where it's the 3 conditions, that thing. It kind of, if you run the run the simulation for long enough, eventually we get some assertions failing, that like things that should be true. We're finalizing 2 inconsistent blocks for some reason, and it's kind of quite hard to visualize and figure out what's happening. And so kind of one of the cool things I'm doing with the testing framework is kind of running the running the simulation until we kind of get a failure, and then kind of saving the history and automatically kind of creating a test case out of that, just to kind of figure out what's going on, which is kind of fun. So yeah, that's
cool. And you don't have any hints about what the bug might be?
No, it's kind of mind-boggling. I've been struggling with it for a bit, and can't really figure it out. So I'm going to keep banging away.
Have you tried hitting everything with deep copies?
No, but that's next, I guess. I'll do that.
Have you checked in your code so that other people could take a look at it?
Yeah, this is in a real state of disarray. I'm going to clean it up in a bit and kind of post. This specifically is just the colored bits, and it's kind of like super ugly and hard coded for just 5 validators. But I'm going to kind of make it more general, and so I can kind of display any number of validators, kind of the fault tolerance growing, and then I'll do that. Yeah,
because more eyes make it easier to spot the bug.
Oh, the bug. Yeah. The bugs in there already. Yeah, at least in one branch in the overlap oracle. So, if anyone wants to go look at it, let me know.
What's the repo?
It's Vlad's. It's on Carl's thing. It's like PC Casper or something.
Yeah, it's a private. It's still private. I mean, I'm hoping to basically come out with. I've started working on it this week, like paper and release the paper and publish the repo at the same time. Both of which are still like a work in progress or whatever. But I think people will like to look at them, and I think it'll be like kind of educational.
Okay.
Cool.
Sweet. Should I give a update? I guess.
Yes, please.
Yeah, please do.
Great. So I'm going to share my screen just because it's more fun that way. So this is just like one example of the testing lang string that I was talking about. And I can just quickly explain. So like B by itself is like mine an epoch. J is join some validators. So we mine a couple more epochs. Then we save this hash, right? And then we're like preparing 1, 2, and 3 are just the validators that are preparing, and then we're committing. And essentially the kind of overall. Actually, one more interesting one is H. H will test to see that the saved hash right here, this like S is save. H will check to see that that's the head. So essentially what we're able to do is in this very tiny, one line thing, we're able to describe the kind of construction of a new chain. And this has multiple forks because you actually, what we're doing is we're like joining a few validators, saving a hash, then preparing committing, and then we are reverting to that hash saved here. So we like do this whole buildup of a chain. We then revert. So now we're back here, and then we build up a new chain, right? And as we build up this chain, we make some checks to see what the head is. So essentially what this allows is for a super like clear and clean way to express the creation of chains and then test a chain's behavior. It's basically it.
Nice.
Super cool.
And have you found anything from this test?
Well, so far I have just been reconstructing my my previous chain tests that were kind of like written out step by step using the actual prepare and commit messages. So not yet, but I'm sure I will find a bunch of issues with the fork choice rule.
How can you be so sure?
Good faith. I don't know. I'm basically what I'm going to do is like figure out all of the edge cases that I can come up with. Then next step would be the next that's like one level of testing where I'm kind of testing efficiency, testing to make sure that the fork choice is always making the right decisions, etc. And then the next level is probably going to be like open Casper test network, where that's where like large scale networked kind of stuff happens. And of course I would love to test better. You can never have enough testing. But I think that's at least those two are definitely in the roadmap. Testing lang and then testnet.
So are you saying that 100% test coverage is theoretically impossible?
That's a good question.
I guess it is for anything that's like sufficiently complex. Like
Yes, it is.
Yeah.
Hey, Mike, you want to give an update?
I don't have a lot to say about Casper.
You can still say some stuff about Ladle, which is
Okay. This weekend, I've been thinking about something called the category of elements. If you have a function from a set to itself, then you can get a category where the elements of the set form the objects, and then you get a morphism from call the endomorphism f, the function f. Then you get an arrow from x to f of x for each one of those, and that's relevant because what we want to do with formulae is allow them to be used inside term constructors. So if you are able to type the things going into a term constructor, then you're able to type the entire term. Also, we want to do the corresponding thing on the semantics side, where if you have a subgraph, then you want to be able to apply the graph homomorphisms from the term constructor and get a new subgraph. And I worked out that if you take a graph-enriched Levier theory, take the free model of that theory, and then apply the power graph functor, you get a new model. And if you consider the image of the functor itself as a graph-enriched category, then it forms this semantics style model that's very similar to the category of elements. So the objects are all subgraphs of, well, all lists of subgraphs of the free model, and then the morphisms take one of those subgraphs to the corresponding subgraph in context. And I anticipate something similar will work for the types. And I think that's the last bit of category theory stuff we need to get the thing fully specified, to get the ladle algorithm fully specified.
Cool.
We can then say, here is what we do, and here's the proof that it gives us a sound type system.
Super cool.
That's
All right. Should we move on to Leibniz stuff, or does anyone have questions for me?
Oh, we can go to Leibniz.
Cool. So I I started working on Leibniz proof a couple weeks ago, but then I found a bug in it, and now I think I've kind of fixed it and have a Leibniz proof for a bunch of these correct by construction consensus protocols, namely the ones that where only new latest messages are viewable. Basically, I have my kind of claim is that I have the I'll have a Leibniz proof for protocols where there's always some protocol state, at least one protocol state, and messages away, which has finality, and for which only new latest messages are viewable by the nodes. I may actually require more, but sometimes it's hard for me to notice all my background assumptions. So let's kind of let me kind of give you the overall story. The definition that I'm using is this one. I'm not sure I talked about it in the stand-up. I call it normally live. Basically what I'm trying to show, and I'm pretty sure we did talk about it. What I am sure we talked about it. What it basically tries to show is that as a proportion of protocol states that are the result of n message propagations, the proportion of them that have safety approaches 100% as the number of protocol messages n goes to infinity. And so it's kind of like a Leibniz proof that says it's kind of like a Leibniz property that is, and just instead of saying, oh, in all possible protocol futures, as n goes to infinity, we have safety. We just try to say that in almost all of them, in the kind of counting sense of almost all. Also in the measure theory sense of almost all. And so basically, and I call this normally live, like a normal liveness proof or something like that. And I think it's interesting because it provides something that I think is maybe weaker than asynchrony, but stronger than partial synchrony.
Yeah, unfortunately, I mean, even if like we can just take it as stipulated that your proof goes through, and it's still not sufficient because computations are paths through the states, and so the paths can thread the needle, right? They can say,
Yeah. Well, I mean, so but the proof doesn't say that all the paths lead to Rome. It just says that almost all of them do, right? I mean, it's sufficient for the value for the proof. It's not necessarily sufficient for liveness and asynchrony. And I mean, like, of course it isn't.
yeah, but that's the thing is like if the computations aren't fair, and in this case they aren't, then what will happen is that most of the computations you run, they go down these weird bad paths, even though almost all the paths are safe, are live.
Yeah, I mean that's completely possible.
Right.
But I mean, and that's not. I mean, that's not an issue from the sense that, like, it doesn't at all contradict what I'm saying. I mean,
No, it
that is
doesn't.
what I'm saying. I'm saying that almost all of them have it. I'm not saying that all of them do. And
Right.
I mean, I can even show that not all of them do. And I mean, it's basically like an FOP impossibility kind of implies that for us.
Yeah, but the thing that I'm worried about is that from the point of view of common sense understanding, just because almost all of them, all the states have this property, like you could still have that almost all of the computations that you run versus the computations that live in some possible space. Those ones just happen to be unlucky.
Sure. It is an interesting problem to ask, which possible, like if I have if I have like a generative model, whether or not I end up with super high probability in one of these almost all states, right?
Yes, that's
And
it.
and
Exactly.
and that's and that's a separate proof obligation.
Yes. Okay. Cool.
Okay. But you're right. That I think there is implicitly some amount of fairness, and I think that as I walk through the proof a little bit, we're going to kind of see that a little more.
Cool.
Um, so the way that my so the way that the proof is going to work basically is I'm going to try to show that in almost all of the states, the number of protocol states that are M states away, like M messages passings away, um, uh, so in almost all of them, that number doesn't grow in N. So the number of steps that are M, as in like mom, steps away, uh, doesn't grow in N for almost all protocol states. And if I can show that, then then basically and I have this additional fact that at least one of them out of the steps that out of the protocol states that are M steps away are safe. Then I get like basically a fixed proportion 1 over some constant for most of them, right? For almost, not most, right? For almost all of the protocol states, uh, which um, which corresponds to the proportion of states, which a lower bound on the proportion of states M message passes away that are safe, and then basically that kind of quickly leads to almost all of them being safe, because basically we a fixed proportion of them are safe every M messages, and as we do like K times M messages, as K goes to infinity, that exponentially just goes to zero, the number of states that are remaining as unsafe. And so the kind of key interesting bit there is to show that the number for almost all protocol states, the number of protocol states that are M messages away is constant in N, where N is like the number of protocol messages in the initial protocol state. And this is a fact that needs to be true as N goes to infinity. And basically the way this works is through this concept of like, that only new latest blocks are viewable. And basically the way it kind of works like this: like whenever I add a message to the protocol state, that message is going to become viewable by all but the validator that sent it. And so every time you add one, every time you add a message, let's call it Q minus one, or I don't know, maybe that's the best. I'll just call it num validators minus one. So the number of num validators minus one, new messages become available. Like possible future states become available every time I add one, and then a whole bunch of them will suddenly not be available. Namely, the ones that correspond to the receipt of messages that are earlier than the messages that were received in the justification from that new message. So every new message, creates new possibilities because that message can now be propagated to new validators, and also restricts possibilities because that new message will contain a commitment of having seen things which now can no longer be seen by the validator who produced that message. And basically the argument kind of is as follows. So let me first point out that this is not going to be the case for all protocol states. It's only because what I'm trying to do is show that it's the case for almost all of them. So kind of trivially, we can say pass a message from validator I to validator J, and then one from J to validator I, and then one from I to validator J, one from J to validator I. So they're always seeing their new latest ones. So they have a really tight coupling of communications, and they're just creating a huge number of messages. And each one of these messages could every time, be be seen by any of the num validators minus one other validators. And so, we add num validators minus one possible things to be seen. But in the meantime, we're only really subtracting one every time we receive a message, because we prevent that message from being seen again in the next step. And so in this case, obviously, the number of messages that could be, the number of protocol states that are m steps away grows and is unbounded in the number of times we repeat this process. Mm-hmm. But what I want to show is that actually, for measure one of the possible protocol states, this is not going to be the case. And the way that I kind of do that is by so let me kind of first let's so let me kind of jump ahead. So there's this one technical piece of the proof that I'm going to jump past for now, and then we'll kind of go back there. So my claim is that if I can represent the protocol states or the message passing in strings, where with string that says okay, validator I sends a message to J, and then validator J sends a message to K, and validator whatever sends a message to whatever, and I have a string of characters, and the characters are independent of each other. Then I can use the normal number theorem to say that almost all of these strings have a uniform distribution of digits or characters.
What's the characterization of independence in this case?
It's all the strings are allowed. It's not that having an A in position I is going to prevent you from having a B in position I plus one, for example. So all of the strings are valid protocol message passing orders. So basically there's some anything in the set alphabet to the power of star, or any kind of string from an alphabet corresponds to a valid message passing. So if I have that, then the normal number theorem basically says that as the length of the string goes to infinity, almost all of them have a uniform distribution of digits. Meaning, every digit shows up equally often, and also it's also the case that every pair of digits, every triple, etc., also shows up equally often. And this is the normal number theorem. It's kind of a really cool theorem in real analysis. or theoretical analysis, or like also like measure theory. So basically from the normal number theorem, what I'm going to get is the fact that I'm going to have a uniform distribution of basically what I'm going to get is the fact that in almost all protocol states, every validator sends and receives the same number of messages, which absolutely is a fairness thing. And this is what I was basically saying, that like, yeah, we're going to see the fairness come up. So by saying almost all of the states, we have this property that each validator sends and receives the same number of messages. That's a quite strong, clearly quite strong of a claim, right?
Yeah. So you could run it the other way, right? You could use the fairness to get back to the normal distribution. You could start.
But I mean, depending on how strong the fairness, yeah.
Yeah, well, that's my point. Is that there's this like a really large notion, set of notions of fairness. So you can get back to some crazy interesting distributions.
Yeah, that's cool. Yeah, and it actually an interesting thing here is that, like, okay, even though I can show that almost all protocol states are live using this kind of case where everyone's receiving the same number of messages, like it's also live if like any set that isn't a majority doesn't receive any messages, but the other ones do have this property. And so, saying that it's safe that live in almost all cases isn't the strongest we could say. I mean, we could in some way talk about more than almost all of them.
Sure,
but anyways, sorry, go on.
No, go ahead. I'm just mulling things over.
Okay, and so basically the story is going to be that in this case, we every time we add a message, we get the possibility of adding a number of validators minus one new possible protocol moves for the next message. But we're actually going to remove some amount of messages, and that amount of messages is actually going to be is going to actually cancel out the additional k plus one, sorry, num validators minus one new messages. And basically the math that I basically require to show this, or what I end up doing is basically making an assumption that there's like some like proportion. So basically you can imagine that if I have 20 messages that you could receive from me, then like you might receive like the first or the second or the third, or like if you have like 50 messages you receive from me, like you receive like it's still the first or second or third. But instead, what I'm going to assume is that like you're going to receive the p times number of messages you could receive from me, ith message. And in that case, you in that case the math kind of works out that in the limit, in most of the cases you get this constant. Unfortunately, I don't have the math in front of me right now, and I don't actually remember exactly what it was. But I'm gonna write it down and produce that pretty soon. But hopefully this give you a relatively clear idea of like the shape of this Leibniz proof. And I think it's like definitely like a great starting point.
Yeah, it's a very interesting perspective. Like I was trying to, I mean, I sent you that reference before. Mike, you might be interested in this as well. So Herlihy and Goubot looked at this from the category theoretic and algebraic topology point of view. So they have what they call higher dimensional automata view distributed consensus protocol, and they can show that it's kind of the existence of certain holes in the space that corresponds to FLP impossibility, and develop some very interesting proof techniques along this. So I guess the my sense was that it's not enough to just do counting, um, and that's exactly the um, the fact that the space is kind of lumpy or stretchy, or I don't know how to describe it, is what your the fairness idea that's implicit in your proof it has to do with that the space kind of clusters or is stretched, and so when your computation is threading through the space, it's the lumpiness or stretchiness has to do with how often or how likely it is to take a particular branch, right? And the fairness is, well, we're going to take all branches equally likely, but that just really isn't the case in most computations. And especially computations that are related to human decision-making processes.
Yeah, and I guess ideally what we'd be able to like show that here's the minimum amount of fairness that we need for liveness, because it definitely is the case that we can't have liveness if we don't have any fairness at all. Basically, a la FLP impossibility.
Yeah, that's right. That's exactly right. Yeah, so it's kind of I've gotten a lot out of the way you're thinking about this. So yeah, I think this is definitely an interesting approach. Just count. So that your approach here has helped me really understand the role that fairness is playing in this. So yeah.
Sweet. Yeah, I'm really glad to hear that. I love being helpful.
Very cool. Awesome.
Really, what I mean is I love pedagogical tools.
No, I absolutely agree. I heartily encourage you to look at the Herlihy and Gubbo research program, because they have some really powerful proof techniques, which will expand the repertoire that you're using here. Cool. Do we have any more for today?
Updates? Anyone? Well, I'd be happy to call it quits 10 minutes early.
That'd be awesome. Hey, Vlad, so are you gonna write up the validator rotation stuff?
Yeah, totally. Yeah, I'm actually right now. I'm writing up like everything that there is to know for the non-economic block, correct by construction, Casper the Friendly Ghost blockchain, and kind of amazingly, the paper is turning out like way shorter than the first time I tried to write it, or when I wrote it like last year when I first did the binary consensus. I came out with this. I was writing it down, and it ended up being like 20 plus pages. Now I have like everything in way less pages. Cool. It's basically because I'm operating at a higher level, and I'm not doing so much bureaucratic stuff, and it's pretty awesome.
Good, very good, very good. Also, Nate and Carl, I strongly encourage if we can get all the code into one place. We've got people who are now fully engaged on writing up various Casper implementations in Rolang. Cool. Again, the advantage here is that the types will give us, so rather than having this weird situation where it looks like the protocol seems to be proven correctly, but the code is showing crazy weird bugs, right? When it's in Rolang, there's at least a ghost of a chance that the type will catch the bug, so that the code you're running is actually the one that's been formally proved correct. That's kind of the idea.
Yeah, I mean, we love formal verification.
Exactly.
Super cool.
Yeah, right. So that they're one and the same, not like, well, we proved this thing over here in Isabel, but we don't know why the Python code isn't correct. So yeah, cool. Yeah, so if we can have example code, that would be really good for the people who are working on the rolling Casper contract.
Yeah, I'm perpetually apologizing for not publishing enough.
Yeah, well, don't apologize. Just publish. It doesn't have to be done. Just
You're right.
has to be done enough.
Right. I mean, basically, I feel like it has to be done enough that it's not going to end up changing drastically in the future, which I think like we totally have at this point.
Okay. All right. Cool.
Right.
And I will post the two most relevant thingies right now in the chat. So.
Oh, sweet. Thank you.
Cool.
Awesome, guys. Really good updates. See you guys next. Oh, you know what? Actually, I think I'm going on a honeymoon beginning next Monday, but I think my flight to New Zealand is in the afternoon, so I might be able to still make the Casper hangout. But then I'll be gone.
Approve of your choice of. Do not bother with Casper the day you are going to New Zealand for your honeymoon.
But for the next 2 Mondays, I will not be on the Casper stand up. I'm not allowed to go anywhere near the internet, really.
All right. We'll try to find it in our hearts to forgive you, Greg.
Talk to Natasha. Okay. Good fun, guys. Talk to you later.
See you later. Bye.
Bye, guys.
Yeah.
Been fun.